Hi, this is Dr. Matthew J. Traum from Engineer Inc. I'll be delivering a lecture in our fluid mechanics course today. The lecture is entitled Uncertainty Analysis in Experimental Measurement, and I'll be talking specifically about the statistical approach. This entire lecture takes about 15 minutes, and what I'm going to do is chunk the lecture into three 5-minute videos. So you could take a break every 5 minutes if you'd like. So this is the first of those three videos covering uncertainty analysis and experimental measurement with a focus on the statistical approach. So the learning outcomes for today's lecture are the following four. First, I'm going to articulate to you the role of measurement uncertainty in reporting experimental results, and that's with a particular emphasis on engineering experimental results. Second, I'm going to compare two approaches to determine the uncertainty in experimental measurement, the statistical approach and another approach which is based on manufacturer specifications. I'm going to talk in detail today about the statistical approach, and we'll leave the second approach for a later lecture, but I will address them both today. And the third outcome is to show you the mathematical underpinnings of the statistical approach to measurement uncertainty, so you can begin to see how the underlying mathematics works to give you the values that you use to report average and experimental uncertainty. And finally, I will define for you something called a confidence interval, which is used in reporting measurement uncertainty, and give you some explanation as to what it is and why it works. Okay, so let's jump into this story, starting out by explaining what it is really that engineers do at a fundamental level. What engineers do, I'll highlight the word here, is to try to understand reality. That is, to understand some function or process that they are interested in measuring, determining, modeling, so that they can improve that process through good and clever engineering design. There's essentially two tools in our arsenal to do this. There is engineering theory and there's engineering measurement. And first, let's talk a little bit about engineering theory. So the goal of engineering theory is to come up with a model, usually a mathematical model, that is representative of what's happening in reality, the situation of interest, but that's simple enough that it can be used for prediction, and so that it can be used to explore design options. So reality is often very complex, and engineering theory has to be simple enough that an engineer can actually use it to determine some meaningful predictions and some meaningful information. And so what we do is essentially strip down the complexity of reality using engineering assumptions to give us the underlying theory. So assumptions really tie reality to theory through simplification. And a great example of the simplification is the ideal gas law. The ideal gas law is a mathematical expression, a simple mathematical expression that relates the temperature, pressure, and density of a gas as the gas is undergoing a series of thermodynamic processes. Now, the ideal gas model is a great model for a lot of different situations. The gas, the air that we're breathing, that is well governed by the ideal gas law. But one of the underpinning engineering assumptions of the ideal gas law is the idea that the molecules of the gas really don't matter, that they are so small that they don't take up a meaningful volume of the gas, and they're so tiny that they never interact with one another. Now, this is a fine assumption so long as the gas is rarefied, so long as the gas takes up a very, very large volume with respect to the volume taken up by the molecules. But as you start to compress the gas, as you start to reduce its volume, the ideal gas law begins to be not such a good approximation, because as you're compressing the gas, as you're reducing its volume, the volume of those individual gas molecules start to become an appreciable fraction of the total volume of the gas. So the volume of those molecules start to matter. In addition, as you're compressing the gas, those molecules begin to bump into each other more and more often. They interact with each other more and more, and those interactions also upset this assumption that there are no interactions between the gas molecules. So The ideal gas law, again, is great if you're trying to model a very rarefied gas, but if you're trying to do something like compress a gas from its gaseous state into a liquid state, the ideal gas law is a horrible representation of that process. As we'll discover in this class, you cannot use the ideal gas law to represent what's happening in a liquid. So that's an example essentially of how theory and reality are connected through assumptions. Now let's look at the other side of the ledger. Let's look at engineering measurement. Engineers run experimental measurements to determine what is really going on with a system of interest. But there is no such thing as a perfect measurement. All measurements have errors associated with them. And so you never know if you're taking a measurement if your measurement has some error that has somehow slightly changed the value that you want, the reality, and your instrument is essentially giving you a measured value that is not equivalent to the real value as a result of those errors. And so what we do to rectify this is we assign an experimental uncertainty to all of our measurements. And uncertainty is essentially a range that bounds reality through our measurement. So what we do is take a measurement and then we assign a range of possible uncertainty values. And if we've assigned this range correctly, if we've calculated uncertainty correctly, then the reality of the situation, of the thing that we're trying to measure, falls within the bounds of uncertainty surrounding our experimental measurement. So let's now talk in more detail about how experimental uncertainty works. That will be the next lecture.